Okay, so we starting to talk about energy-based model training. So if you recall last time, we talked about energy-based model. Those are basically probability models that are unnormalized. So they defined by energy function. Without usually you care about not normalization. There are conditional, there are some unconditional. So we could do both with an energy-based model. And we can do sampling from energy-based model using unnormalized. So there are methods to do that. They are not necessarily efficient, but if you have enough computational resource, you could sample from that. So basically, we are especially interested in continuous models. Like Langevin, right? So that's a sampling algorithm. Essentially, the sampling you can have both depend on the energy function or depend on the gradient of energy function, right? So Langevin is similar to optimization. They depend on the gradient of energy function, and then they can sample from the energy model. So that's about sampling. Today we want to talk about training these energy-based models. So how do you train these models? Okay, so let's go over. So because these are probability models, energy-based models, so we can use a maximum likelihood estimate for training such models. The other one is a negative log likelihood loss, right? So minimization. So you can either maximize likelihood or minimize negative log likelihood. And for earlier classes, we talked about softmax with logit, which is basically the maximum likelihood estimate, which for multi-class classification. For energy-based models, you can do the similar thing, except you want to assume the normalization is difficult to compute. So we want to avoid that. So basically, this is a background, which we'll talk about. Then we talk about the gradient of this maximum likelihood estimate, as well as contrastive divergence, which basically approximate maximum likelihood estimate for energy-based model learning. Then we will talk about actually the topic we already looked at, which is softmax with samples. This is where we talk about at least 2 lectures. We talked about those. One is contrast loss for learning representations. The other one is when we talk about the CLIP. CLIP model uses contrastive loss to learn alignment of text and the image. So in the more general setting, we call that sampled softmax. So this is something which can also be used to do energy-based model learning. And related to the sampled softmax, there is something so-called noise contrastive estimation, NCE. This is a surrogate. Essentially, sampled softmax is treating that multi-class classification problem. If you recall the contrastive loss we talked about earlier. So those are multi-class. Contrastive estimation, NCE, is treating that as a binary class. So this is basically a relation of these two. It's kind of few representative. Again, none of those are perfect. And in reality, energy-based model can be tricky to learn. So people, at least the modern ways, shifting away from that. For example, GAN is one example we did. And we will also talk about next week, we will talk about the diffusion model, that's the same thing. And related to this lecture, next lecture, we'll talk a slightly different related method. We just talk about the score learning, right? So if you recall the Langevin use a gradient of the energy. Gradient of energy means to do sampling. Gradient of energy is called score. And this can be learned directly. So this is something we will talk about next time. And after that, we will talk about the diffusion model, which also related to the score. Okay, so so we are now we are doing. Now let's just recall the energy-based model which we talked about last time. We will look at the unconditioned, but adding condition is not a problem for all the methods we actually talk about in this class. So we could add condition without issue. But we look at the unconditioned just for simplicity when we write the notations. So there is we write as in the case of continuous variables. So we have a partition function z, which is an integral of this exponential of minus energy, right? So basically, this is the model and the partition function. Clearly, partition function is tricky, right? So for a conditional model, yeah, this is just recall that last time, but we are mostly focused on the unconditional in this setting. Okay, so the first one, so just for simplicity, yeah. Otherwise, they are all pretty much the same. Yeah, so basically we talk about the unconditioned, but the same idea, just doing condition. So for all three methods, okay, all three methods should be okay. Let's look at the maximum lifespan estimate. So given this training data, which comes from we call that P data, which is the truth. We want to maximize the likelihood. So this is a classical statistical method, the most important and the most widely used method for statistics, where you want to maximize this, right? So basically, this is the method. You can also say equivalent negative log likelihood, NLL, right? NLL is a loss function which you minimize. So basically, NLL minimization is written down here. These two are equivalent when you plug in the energy-based model formulation. So these are the same, just minus, minimize minus log likelihood. So these are the formulations. If you look at this, right, so you are just looking at that, you essentially you are trying to minimizing the energy function, right? But it's a probability model. It's not only an energy function itself, because energy function is unnormalized. Therefore, it has to be subject to this this partition function, log partition function, which is actually to do with the it's a probability model. Yeah, basically you need to, and this is the harder to deal with term. So we will talk about that. And this term we try to avoid computing explicitly, right? So because this is hard. If this is a neural net, right? Think about if this is a neural net, how do you get the integral over the continuous in high dimension? It's very difficult. So in large discrete or continuous space, computing this is hard. And then what we do, right? So what we do is the following. So we do this. First, we will look at the maximum likelihood estimate, right? So first, in the maximum likelihood estimate, the log likelihood is basically this. This is coming from the previous slide. So this is the form, and we take gradient. So the gradient is the following. So basically, because all the methods in machine learning, when you do the training, we are using first order gradient-based methods, right? We can plug these together with something like Adam, whatever. But essentially, the key of all these methods, including like momentum Adam, they all based on can be computing the gradient. So we compute the gradient. Gradient basically, these are two terms, so we take a gradient for each term. This one is easy in the sense of why should it be the observed data. This one is doesn't depend on the observed data. because this normalization, but it depends on theta. So if it depends on theta, you need to try to work with that. Basically, observe data. So this is easy, and this is the tricky part. We write down this optimization. Basically, log of this optimization, you take the gradient, log becomes 1 over z. And this is a z, this is optimization. Okay, so basically this one is 1 over z gradient with respect to z. The z is here. This is normalization constant. Then what we do is we take derivative with this guy, right? Take derivative with this guy is a minus because this is a minus. Exponential coming out, this is a chain rule and a gradient of f. So basically, this is the formula, right? So if we look at this formula, what this is, if you look at this guy, right? This guy is a probability of energy model. So basically, this is exactly probability of an energy model. So what does it mean? What does it mean? It means that this guy is a probability. This coming from here, right? So this is a definition of normalized probability model and integrate with your gradient. And we can write that in a more expectation case. I mean, this is say expectation of y tilde drawn from p theta. This is just a definition of this guy. And so basically, this is the exact energy-based gradient. So what does that mean? This is the formula people use, try to come out with algorithms that can do maximum likelihood estimate. This actually says the following. So if you can draw a sample from this current model, right, then you can actually compute this guy. You can really draw exact sample, for example, using reject sample. If this is something you can do, then once you do the sampling, you can plug in this sample to be this guy. And then you can have estimation of the gradient. So essentially, it turns about this normalization to a sampling problem. And this particular sampling, the hope is you can use unnormalized sampling method, which we talked about last time. So this connects this training to the sampling. That's why we first talk about the sampling in the last lecture, then talk about training in this lecture, because you need to do sampling in order to compute the maximum likelihood. Okay, so now this is a key formula, right? Basically, the main thing is that the first one is easy. This one is observed data. So you just take gradient. Assuming you have energy function, neural net, you can just take gradient by using PyTorch by prob, right? But here is something, again, there's a gradient, but here is y tilde is not observed. It's actually the generated data from your current model. So basically, the main thing about that, we will come back, right? So sampling from this is become a key. And this is coming to the last lecture. So let's look at the maximum likelihood estimate in this. Essentially, I mean, the derivation, you can just do a few lines, but you can also try to make a note on that. There's a positive phase, there are negative phase, just looking at the slides, then you will always know that what it means. So positive phase is a data, gradient of a data. Negative phase is a gradient of your generated sample, right? So first you generate a sample from the current model, then you take a gradient. So this is the maximum likelihood estimate. So basically positive phase, lower energy on the real data, right? Real data becomes more probable. And you can compute from observed training data. So that's easy. Negative phase, the main thing is raise energy on the current model. Essentially, it's pulling away from the current model, pulling towards the real model. If you think about this, something like a GAN, right? GAN is also doing similar things, but it's not using a likelihood. It's using a generator, but that's a very similar thing. So generator will generate your sample. So this is where GAN becomes easier instead of you are sampling from a likelihood, sampling from probability model in this. So it's very similar to, if you look at this, very similar to WGAN. you can think about you have a positive, you have a negative, but your generator is modified, right? So recent energy on the current model samples, right? Generated sample become less probable, but then so you can interpret it that way. This need to be implemented by sampling from p theta, the current model, at each update. And this is actually the harder part. If you look at the last lecture, of course, there are many more sampling methods, but none of that can give you exam sample easy. If you're doing rejection sample, last time we talked about that kind of sample, except if your acceptance probability is low, this can be very inefficient. Or you can use some other Monte Carlo methods, basically MCMC, Markov chain Monte Carlo, right? Those methods, like Langevin is one example we give. This is not the only one, but we use that for our lectures because it's related to multiple lectures. So, but then it takes a long time to converge. This is what we shown last time. So, but anyway, so the thing is you just need a sample from that. Okay, the intuition is analogous to GAN. You're pulling towards real data away from generated data, right? Especially WGAN, if you look at this formula. Anyway, so this is a kind of thing which we want to implement if we want to do maximal likelihood. If we cannot sample y tilde precisely from p theta, we can only do approximate sample. And approximate sample is something which we want to talk about, so-called contrast divergence. It's a Hinton has proposed this method. They have a bunch of papers, as well they have a certain model like Boltzmann machine and so on. In the early days, they try to use that to optimize. So contrast divergence can be regarded as a practical approximation to the negative phase of maximal likelihood estimate. Basically, it works as follows, right? So for each data sample, you can initialize the chain from that's what actually proposed in the CD. But here we also add a proposal distribution. This proposal distribution actually shows up in the others. Essentially, it's just some distribution that can covers your distribution. You can thinking that as using like a rejection sample, you have the sample from one distribution, or some other, they are sometimes called a noise distribution. In both sample softmax and also in both NCE it comes. So basically I will add this guy. You can sample starting from this guy or starting from this guy. Then you just run the chain. Run K unnormalized sampling. In our case, we talk about Langevin. You can replace that by some other method. There are discussion in the original CD. They are trying to using like a Gibbs sampling or other methods, to solve that. But we here we just say let's just focus on Langevin. Okay. Obtain the short range. You just run that for k iterations. Then that's all, and then you are done. So this is this approximate sample, right? So you are unless k equals infinity, then you get the convergent samples. Otherwise, you are approximate. But typically, according to CD, this is sufficient to get you a good estimate. So basically, that's all. So basically, you compute. Basically, your loss function is f theta data minus f theta yk, right? Then you take derivative. Once you take derivative, the PyTorch will get you the result. So the update. Okay. So basically, this is what it is. So this is called CD contrast divergence. Yeah, basically, the one sentence is in the maximal likelihood. When you take derivative, you have a positive, negative phase. Positive from the data, negative from the generated, and CD try to mimic this negative phase by using Monte Carlo, Markov chain Monte Carlo methods, and unnormalized sampling methods. right? And in our case, we will use Longevin. So okay, so that's about it. Now let's see what implementation. I mean, implementation is pretty straightforward. You have a CD loss, right? And you have a mini batch. You have a negative. Negative. You just starting from this word proposal. You're starting to draw. Lower the energy on data, raise the energy of these samples, right? So basically, and then you try. Essentially you try to move your generative model. Actually, it's not generative model. It's a probability model, right? It's probability density model. It can be do generation through sampling instead of the other type of generation we talked about. And this approximate maximum likelihood estimate, it's approximate, it's not exact. We cannot do exact maximum likelihood estimate as we mentioned. So it's because it requires exact sampling, or it requires computing of normalization constant. Neither is feasible. So this is this is basically the algorithm, right? So if you look at the actual implementation, it's pretty simple. This one is a Longevin, right? So you start with pi, you do this negative sample, you just do a Longevin sampling, starting from and use let's say 10 steps. This is a Longevin. Longevin is the goes gradient of your current model, current energy, and then you're adding a noise, and you just repeat that 10 steps. And then your loss is this guy, right? It's the energy of the true data minus the energy of the negative data. So that's what it is. And then you just, so basically this is the PyTorch implementation, which essentially is identical to the one we talked about earlier. So this is a example implementation of a contrastive divergence. This sampling, you can use other sampler. So not necessarily Longevin. We use a Longevin just for illustration, but the CD require you to go to other samples, right? So there are, but hopefully, the idea is pretty straightforward. The idea, as long as you know how to compute the gradient of a maximum likelihood estimate, the gradient of negative log likelihood, and as long as you know how to sample, then you can do that. You can do this contrast divergence as approximation of maximum likelihood, right? So minimize energy on the data. Again, you are in the contrast is where you are pushing your energy up on your current model state. So you're moving, and this allows you move your model towards lower your current model and the probability, the likelihood, and moving up your real data's likelihood. So there's a contrast. Okay, so let's look at the empirical experiments. So we will look at these experiments, and then after that we'll move to some other methods. So experiments, you have just simple experiment. This one it's a 2D mixture of two Gaussians. So we will see that. Model is energy network, right? So it's just a neural net. It's a MLP. So in the example, so we and then we will say, okay, MLP in 2D. Of course, 2D you probably can try to integrate because it's not too large. But for the sake of what we are looking at, we probably say not. But when we evaluate, we could, because it's just 2D, right? We could actually compute this normalization constant. We can normalize that on a grid, small grid in the 2D, and compare so-called TV distance of these two distributions. Then we can see how well they do, right? Noise distribution. This one is used for in our case, they actually used for both the later two methods we talk about, the sample to softmax and the NEC. They both require noise distribution, but here we can also use that to initialize the Longevin chain. So this one is a known distribution. typically. Okay, it's a known distribution which we use, which can be either for the longeving or for whatever other methods, as we will see later. So this is basically. Here is, just the 2 TV distance is just, integrated over this 2 dimension. So basically just the density, you compute the density, right? You take a difference. One thing I want to say, right? So for probability model, one nice thing, once you normalize that, you can always have different ways to evaluate. One particular way to evaluate for some likelihood, right? Maximum likelihood, log likelihood of your data, which is always regarded as a very good metric. This is also the way a large language model is trained and sometimes evaluated, the prediction. For other generative model, like a GAN or like a later diffusion model, it's much harder to evaluate. It's actually trickier. People come out with different metrics, but they are not as clean as if you know the density. So here, because this is 2 dimension, we can have this density, so we will be able to do that. Here is the data and noise distribution. So it's just a mixture of 2 Gaussian. It's a simple problem. It's just for illustration. So this is the true distribution, 2 Gaussians. And this guy, if you think about this guy is larger enough, this noise distribution, right? It's larger enough to cover these 2. Yeah. So basically, this is just for illustration. Okay. It doesn't. If your noise becomes smaller, what happens, and so on, right? So you can ask, but so we are not counting that. We are more interested in the other part, the longeving steps needed, and so on. So left is the true, right is this noise. Noise is essentially, in our case, we sometimes will maintain the chain. When we do the longeving, sometimes we will starting from this initialize from this noise distribution, random sample from this guy, then draw something. Because this covers this guy, because this covers this guy, so you have a probability and go into here, you have probability going to there. Actually, if you look at this is centered right at 0. So if you look at that, from here, it's closer to this guy. So you are more likely to initialize it to this region than that region. So that is one thing, actually, longeving is very difficult to jump from one mode to another mode. If you run the longeving, because gradient of this guy is it's almost flat. And then here, essentially, it's just going around a lot and until at some point it jumps. But here is the same. So Monte Carlo chain, Markov chain Monte Carlo, they always have this kind of issue about jumping over different modes. This is something which we will see, and it have some effect. But here it's not entirely symmetric, so that you will see it closer to something than the other. And this will have an effect in terms of MCMC. So here is the training loss, right? So you have 10 steps versus 100 steps, right? Training loss, you can think a little bit as an approximation of your MLE, the or negative log likelihood, right? The lower, the better in some way. Here you can see at some point, if you do this one, this actually doing a little bit of overfitting, because when you do 10 steps, it's not running too far away from your initial points. So basically, it's a little bit. And this one, it saturates with more steps. But basically, this is a kind of, basically you can train that. Turns out, but essentially, these are different, right? So basically, steps matters. In fact, you would trust more of these guys, right? Training loss eventually flattens at some point. This one keeps running. Again, so you can think of that as like overfitting because you are too short. Yeah, it's okay. But essentially they're different. So that all it says is here's what you get. This is yeah. So basically, this is true density. If you run this one, actually doesn't converge well. It converges to one mode. When you have many more steps, you converge better. So TV norm, if there's a completely orthogonal densities, the largest TV norm is 1. So that is when they do not overlap at all. 0.2 is somewhat overlapping if you look at that, right? So, but it's not ideal. So as we'll see later, you can get better than TV normal than it. But this one is starting to become reasonable. So essentially, the number of steps matters, all it says, and it's actually quite sensitive. So Langevin runs, they were sensitive. If you look at our previous lecture. Right, so it's sensitive to step size and the number of steps. Step size is a learning rate, right? So basically, they are sensitive both, and here we just pick something, and it actually runs not that nicely. So I tried to play a little bit with this. I found it's pretty sensitive. So even for this simple model, I mean simple two-dimensional mixture, but nevertheless, it can learn and learn not great because if you look at this, this is still not quite right, but somehow I starting to converge, right? But basically, it's sensitive. All I can say is, so if I have a conclusion about this, again with a simple example which you can see in the notebook, one pros is of course is it's using the maximum likelihood estimate, and this is always people like. If you can do that, people like that. So this has a lot of nice probability in statistics, but it using the MLE gradient by approximate the negative phase sampling. So this is works in continuous space without require normalization, right? So this is something can generate implicit negative samples from the current data. This is through the Langevin. But basically, so this is says it's related to, actually, if you are one sentence, it's just approximate MLE, right? Cons, of course, it's sensitive. Like if you think about it, it's a short run, because if we see 10 step versus 100 step, 10 step doesn't really even converge. Also, it's pretty sensitive. I've already tuned a little bit about this. It's very sensitive. But if you are interested in this, you can actually go to the notebook, try to play around with settings, and then you see it's a pretty sensitive. Yeah, and it require a lot of number of steps. 100 is a lot, right? And you can play with the step size. You can play with others. Also, there's some regularization. Computational is very expensive. If you think about step size is 100 for a Langevin run, that's a fairly expensive inner iteration per outer iteration. Each outer iteration is kind of like a maximum likelihood estimate iteration, one step, but you require 100 steps of a Langevin run. So that is actually pretty unscalable if you think about that. So this is the bad things about this. It's too expensive, and this is why it's hard to scale. So although there's a paper about using Langevin, the CD is quite a while has been there. Langevin they are playing around. Langevin also known quite well, but the Langevin plus CD, there's some actually it's a recent paper a few years back. The paper, and it's actually pretty recent. But I don't believe it's as widely used compared to other methods, like because as I said, it's kind of sensitive. But anyway, so this is if you want to do maximum likelihood estimate, if you really say, oh, this is what I want to do, and this kind of a CD is the method which is used. So this is something. Now let's say, okay, are there other methods for maximum likelihood method? Turns out we have already seen one. so-called sampled softmax, which is basically contrastive loss we see before. So more formally, so we will start with that more formally this time rather than talk about as contrastive loss, right? More formally, so what happens is the following. So we can have a so-called positive data. Again, you have a positive and negative in some one, right? So think about the maximum likelihood. You are running negative data from your current model, which is tricky. But you can also run the negative data from the proposal, right? Think about that. So what do you do with the proposal, right? You can either do using rejection sampling, but then that can be tricky because rejection sampling, the acceptance risk can be very low. So that again becomes inefficient. So in the sample softmax, we are doing the reject instead of doing as reject sampling, so-called important sampling, important weighting, so that we sample from that by taking the ratio of the current model and this guy, so that you are weighting that. So basically, you define this guy. This guy, when you do an exponential, right? Exponential, and this guy is divided by Q. So become then essentially it's a current model divided by the sampling, and then this is called importance weighting, and this kind of importance weighting we have used in quite a while, and a lot of time in the machine learning, and then essentially you change it from this guy to this somehow this guy. So basically, importance weighting is a kind of a thing in disguise in the sample softmax. Then you just use the softmax. You are adding one term here. So you can either using this guy divided by this guy, but then that will be unstable because Q can be far away from your this guy. This one can be, when you take expansion, they can be very small. So the ratio can be bad. So you're adding this guy so that the ratio is always bounded. So basically, this is where the sum for the softmax comes in. You have a positive sample, negative sample, but you're adding one sample of negative, positive here to stabilize your computation. So I listed here, which is. So this softmax appears definitely in many places. We know at least it kind of works in the sense of you just appear in the contrastive learning. And in contrastive learning, you draw a uniform distribution across your negative data. You get a pool of negative data, you draw uniform, and this one you can say it's just drawing from certain distribution, which is kind of there. So basically, this is a form which actually does. So in the training. So if we do that, right? So what do we do? Right? What we can do? Turns out, if I do this, adding this one is good because adding this is stabilized, right? But then if I ignore that, just look at this, one M is large, right? Very, very large. And this one probably is mostly dominating. Only rarely this one becomes important. So you can look at this ratio. This ratio turns out when M is large, it is like maximum likelihood estimate. So basically, this one is M times the partition function, essentially. So this is basically what we want to show next. Including the positive in this guy here, right? So it's trying to stabilize. So asymptotic MLE equivalence of a sampled softmax. As M goes to infinity, sampled softmax becomes equivalent to MLE. So this one is, I just quickly give the proof. Proof is not too complicated. It basically just say, it's a more stable version in the finite M case. You are sampling from proposal, which you are stable, right? This guy, right? This is what this is a logit, and this is the energy minus this guy, right? Essentially, why you want to minus this guy? Minus this guy, you look at this guy, right? This becomes this. You take the expectation of this guy, it becomes this guy, right? This one cancels this. So essentially, if you look at the minus L and this guy, this cancels, then essentially this one. Basically, this becomes partition function. So this one is say, when I draw samples from Q using summing of this guy, it's become a partition function, right? And by law of large numbers, this is my negative samples from showing in my sampled softmax, right? Divided by 1 over m, and then you goes to that, go to z theta, and then sample the denominator. Essentially, this guy goes to mz theta. So basically, this is what it is. And basically, you can look at this loss function. This is your sampled softmax loss function, contrasted loss. And given this term, it goes to minus this guy, this coming from here, right? And this guy, I will ignore this guy because the mostly will become this and log m plus log z. So this become yeah. So basically, essentially, yeah, this one and this term, because it's dominated by this one, if you add this guy, it's 1 over m something. So basically, yeah, becomes that. So essentially, it's actually converged to this guy when you do algebra. And then you are using basically the sampled softmax, right? So it's essentially, this guy is this guy becomes, right, log q, yeah, this one plus this guy, right? So basically, yeah. Yeah, basically, yeah, basically the contents mean it doesn't depend on theta. So when I say constant, right? Because this one is a theta independent, right? So basically, yeah, this doesn't depend on theta. So only theta dependent terms is the same as maximum likelihood. So this one is negative log likelihood. So basically, I mean, yeah, this is just a quick derivation, but the point is that as m goes to infinity, sampled softmax is equivalent to MLE. So we will look at the same experiments, the same proposal. We have seen that proposal earlier, and the same two component Gaussian mixture, right? And if you look at that, again, it's a difference. This one different. One thing we all want to mention is because m is different, right? So normalization, you have to remember they have log m difference. So it's not surprising they are different. But what also you want to see is that in reality, you actually yeah yeah, basically, but basically, eventually they will converge but usually, when you goes up, it should be better, right? So this is what we want to say. Examining the same setup, training curve, just to say, m matters in some way. Okay, m matters, and because you have if you look at yeah, maybe I will just show. If you look at the denominator, you have a plus log m, right? So when your m increases, you are expecting this one going up. So basically, because of a log m. Yeah, I didn't try to compensate for that factor. If I compensate, then they will probably overlap more. But basically, just say, this matters. But here is what it is, right? If you think about the long join, this one actually more efficient one thing, right? If you think long join, it's 0.28 or something, right? So for the CD, this one is the true density. Here, actually, the m equals 1 is pretty efficient, right? 0.1. If you increase, you get even smaller. So 8 and 64, at least for this example, doesn't make much difference. But they still decrease a little bit, but essentially it's about the same convergence, right? But basically m is 8 is sufficient. Here m equals 1 is the TV norm is already better than the CD example. So essentially, at least for this example, this works pretty well, pretty stable. It's much easier to tune, let's say, than Longevin. So from that perspective, again, it's not surprising because very similar methods has been used for the for the contrastive loss, right? So it's a very stable, good empirical results for when m is large, right? So basically, and then so that basically, these methods can also be used. It's kind of a little bit more stable, and at least for this example, it gets some good results. So sample the softmax summary uses a positive versus a sampled negative softmax objective. It will get you somewhere. It's at least get you something stable. So that's one thing. And the some related methods, the contrastive loss, right? It's very, very similar to this. It's used in practice. Again, it's because of stability. If you think about that, it's stable to train. That's why it's used. And we can show that when the number of negative goes to be very large, the infinity samples, this one can get you the MLE. This one is similar to the contrastive divergence, right? They're just using a different methods. This one doesn't use rejection sampling. You can think about CD and using rejection sampling to do sample. But this one doesn't use rejection sampling. It's actually use this kind of importance ratio plus a stability term. So this is how it works. And cons is effective depend on the choice of distribution Q. So it's not a free lunch. Basically, sometimes you have to say, I mean, if Q is too large, too different, what happens, right? Then the signal becomes very loose. So even in the contrastive learning, you have a similar issues. So how do you select negative? And actually, there are papers talking about what is the best way to select negative in the contrastive learning, and that will be pretty much related to this problem. For finite m, right, still approximate, so we don't have an exact. We never have an exact MLE formulation. Larger m give better approximation, but increase the computation. This will be the same as like in the CD. So basically, So basically, this is another method. So one can look at if you are interested in training a energy-based model. Approximately, you say, oh, this is approximately maximum likelihood, and this one is 1. So I think the last, this is about the 2 methods we talk about. The last one is very similar to the contrastive learning or sampled softmax, but it uses binary classification instead of multi-class, right? Contrastive, you are still trying to mimic the maximum likelihood. You generate many negative examples from the distribution, from a proposal distribution, and then you do the importance ratio to make it like the sampling from your current model, and then you can think about the number of samples. Then you can think about its likelihood is weighted by these samples. So it's a softmax. Instead of softmax, we can also treat each. If you think about this, we can treat each of these sample pairs, negative and positive, as a binary classification, right? If you do that, this becomes NCE, right? So noise contrastive estimation. So if you come back, right, negative maximum likelihood estimate, this is the loss function you need to implement. And this one taking gradient with the samples, right? But the normalization is tricky. So what do we want to do? NCE change the hard density estimation into data versus noise. Noise is like the proposal distribution, which we have used for sampled max, softmax. And this one is a data versus noise distribution discrimination that will cause. So you introduce a no noise distribution. Again, this is the same as a sum for the softmax. This one has to be known. You can draw sample from, and then and the same distribution also appear in rejection sampling. Compare true samples against negative samples, and this one sample actually is coming from Q, right? So if you compare this guy, then train to a binary classification objective. So this is the key. Binary, you don't need normalization. And we will see how the normalization comes in this particular case. It's actually clever. You can think the trick or whatever. So NC is a surrogate loss. It's not maximum life anymore. It's more about binary classification loss that avoids normalization. This one, if you think about that, binary classification is also in the GAN paper. It's a discriminator, right? This one also has a discriminator, training discriminator. But GAN training discriminator also train a generator directly. But this one say, oh, discriminator is related to the density function. So, and you do need also GAN. I think always the proposal always is a current distribution. Because you have a generator, the sampling becomes easier in the GAN. Instead of you have a probability model, the sample is tricky. But this one is a fixed distribution. So NCE. So let's say you have this setting, right? What is your discriminator looks like? Suppose we mix one data sample and mu of proposed samples, right? And then you have this formula. So basically, this is just mixing. This guy is the class about your data sample. This one is a proposal sample, right? And they weighted approximately. So basically, this one. So, and now this they place that with binary classification, right? Binary classification, whether it's coming from this sample or coming from this sample. You ask this question. So binary, yes, no, right? And this one. So for each one, you can ask each belong to. Same in the GAN. For each one, you ask it whether belong to the generated sample or the true sample. GAN is the true sample, generated sample. Here is a true sample or proposal sample. Using normalized EBM, this guy is become this guy, right? The logits, classifier logits usually is just this divided by this take log. This is where the logits, and once you have that, this classifier is e plus e to the minus logits over 1 or something. So that becomes logistic or sigmoid transform. Here, you know, these are logits. These logits will be minus f here, minus, this comes from, these two cancels, right? Minus this guy, minus the log of your partition function, minus the log nu. And if you look at this logit, it still contains partition function, right? So then what happens, right? Now, what's nice is the following, right? This partition function, although it depends on that partition function, it's true, still there. This is a no, but then, you know, it doesn't really matter. But essentially, if you look at this term, it doesn't depend on y. Also, I'm learning a classifier. Logits going to a binary classification loss, BCE loss, right? BCE, some binary cross entropy loss, working on these logits, treating as a classifier, it can train even, I will just absorb it into a parameter in this classifier. I don't know, but I can learn that. So that's the whole point. And I will say, oh, you know, normalization is just another parameter. So basically, that's the key. Key observation for the NC is these are logits. Logits can be learned using BCE, right? And logits contains this guy, but it's y independent. So if you add this as y independent, you just add a b, right? B essentially is a bias that can be absorbed into learning parameter. So basically, that's the key part about this. So the logistic function in the previous example, right? It's harder to learn the log, and now it actually becomes learnable. So basically, it's just one parameter. That's all. Because it's a classification problem, the whole thing can be learned simultaneously. So this is a key observation, and this changes the role of your normalization. Normalization used to be in your loss. Here it's in the model. Right, so it doesn't, it just increase one dimension, B. So that's all. So practical parameterization, you can define new energy big function that absorbs the offset in the NC logit. So that's basically, you can think about this, right? So basically this is a new, you can say, oh, this is my starting point, and this one, the key part is independent of y. Actually, if you think about the independent of y, it doesn't really matter in some sense. If something is independent of y, its energy and energy plus a constant which is not dependent on y, it can be dependent on theta, but it doesn't matter. So it's a really normalization. So you can introduce a learnable parameter b, that can be done. And if a conditioned model, right, this one b, it will be bx, depend on x. But for our purpose, we can say, oh, just absorb into theta. Theta already have a translational parameter. You can think about just a typical neural nets, right? You could have b in the final output in your logits, and then it's absorbed into your theta, the network. So essentially, we just say, oh, here is a new one, and the logits. Now with this new learnable parameter, either explicitly or absorb that into the bias term in this guy, right? It's become this guy. So we are just using that, just absorbed into theta rather than introduce additional parameter. But either way is okay. So the NCE classification now becomes, this is your new model, right? So this is a known, so it's okay. This one is what you want to learn, and become this guy. D equals 1 is this guy. D equals 0, which is coming from the proposal distribution. This is coming from the true distribution, right? And then is this is basically logistic model, right? Basically, yeah. So sigma, which is the sigmoid transform associated with the logistic model. And then, yeah, so that's what it is. And this one is different. It absorbs this additional term into your parameterization. So this is one thing. For us, we, as I mentioned earlier, you can add another B. But we say, this bias is already in your data. For example, you have a 2-layer MLP. And if your top layer has a bias term, right, then you don't need to add another bias term. The bias term and the bias plus bias is the same as bias. So basically, it's all, so we just write the data. Another thing is a Q is known, right? So this is a whole known distribution. If this is a Gaussian, y will be something like y squared, right? Divided by whatever the standard deviation you have. For simplicity, we will drop this new. So basically, we just treat, essentially, if we drop new, you can think energy-based model, this one is ignored. So the main thing is this can be ignored because it can be absorbed into the learnable parameter. And this learnable parameter, it doesn't depend on y. So therefore, it doesn't affect your normalization. It will get you, basically, you can be renormalized, can be absorbed into the z. So it doesn't really matter. Yeah, so this term. So anyway, so this one is, yeah, we just dropped the row, and we just still looking at the logits will be minus f minus log q. That's what we want to say. Here is my logits. By ignoring this normalization, because we can observe that with a known Q. This is the same as that of sample to softmax. Sample to softmax has exactly the same. Essentially, you have your energy function. You have ratio. If you take exponential, it's a ratio of f divided by q. Q is a proposal. Treating this as proposal. Okay. Now what you can do is the following, right? So I have you can say this one is just mimicking the sample to softmax. This is one positive example. You can draw m negative example, just like sample softmax. But instead of treating that with the softmax as a whole, you're treating that as a binary classification. Basically, it's like m binary classification problems were positive versus each of these negative. So essentially, it's one-to-one pair. You added that for all these m. For the experiment, we just take m equals 1. So we didn't really explore because it just balanced these two. And nu also we will take that to be 1. But basically, you can do something very similar to this sample to softmax, except instead of a softmax, you treat that as a binary classification for each binary pairs. Right. This allows us to learn this without computing normalization. So this is the whole NCE derivation. Basically, use this guy, and you try to learn a logistic loss. If I use this logit, this is basically NCE loss, right? By BCE, this binary cross entropy loss. So here is that. Yeah, this one is basically binary cross entropy with 1. This one is the other direction, but basically this is divided by Q, and negative also divided by Q. And the main thing is this guy comes from the data sample. This guy coming from your Q sample, and then you do that, you just have this loss function. So that's yeah. That's all it is. Yeah, basically, yeah, basically that's about it. Yeah, this one you can also write in BC. BC positive, BC negative, right? BC with 1, BC target 1, BC with target 0. So this is that. So okay, so let's look at the training. So for the training, it's yeah, I just use the m equals 1. So for this one, so it really doesn't have much. We can try m larger than 1 and so on, but here is m equals 1 for each. And yeah, basically, again, this loss function is different from the maximum likelihood. It's a binary classification loss, right? Here are the empirical results. These are the two distributions. The left is the true density, right? The right actually it goes a little bit to here, yeah. But basically, but still, the TB distance is 0.18. If you compare with m equals 1 in the softmax, this one is not too bad, right? So, but we didn't do the more. But also it's actually if you just look at the TB distance, it's better than that of the CD with laundering. CD with laundering, the shape is not quite right. Here, their shape is kind of right. So basically, this is again, none of this is perfect in some sense, right? They are approximations. And here, the main thing about this one, you can think about that. What happens, right? So why, it's an exact formulation. But if a Q is very farther away from the truth. Then what happens is there's not much signal. This situation is, let's say we have a Gaussian, right? If you have a GAN, you can start with a Gaussian, the Q. And then we already talked about that. In the case you are starting, the two ratios, the discriminator almost always 1 or 0. So it doesn't contain a lot of information when you take the gradient. And things like that will happen here. So essentially, if your Q is very far, in this case, it's 2 dimensions, so not too far, but it's already pretty far. Q is a Gaussian, and this one is much narrower, right? So you have a large ratio. So for both of this part, it's a distinguisher has to be in the true density. If you go everywhere else, distinguisher has to be from the Q, the proposal density, noise density, right? So it's not that great. So therefore, the signal becomes not that much. This is what you see here is not perfect. And this one is similar to the issue of GAN. And all these issues have this kind of problem. Your approximation may not be that great. So if your approximation may not be that great, then you will have things like this. But basically, it's one method which can be used in certain situations, right? It really depends on your application whether it can be run, but it avoids this normalization. So compare with the normalized EBM density with the true density. Report dV distance on that, right? So basically, yeah, this is dV distance. Okay. So if I want to say what the issues, pros of course is no explicit normalization. It turned density into binary classification, turned the normalization actually into a learnable parameter. So this is a nice trick. So you can ignore this normalization once you turn it into binary classification. It's very easy to implement. You just need to implement the BCE loss, right? With a known proposal. So basically, these are the advantages. Cons actually, one thing is, people generally like maximum likelihood estimate more. Usually, those are more efficient. Usually, so this is not exactly MLE, although that's this is one thing. But in practice, right, what's wrong with this loss rather than maximum likelihood estimate loss? This is exactly the issue which we come out before, and the Q is sensitive. And this actually also appear when you do the contractive loss. We didn't talk too much in the sense of a contractive loss, or at least or in the sampled softmax. They use the same logics, but sample softmax try to adding everything beneath your normalization, right? It's a little bit more robust. Here, but that one is not exact. That is approximate. Here, this one is exact because from binary classification perspective. But if Q is far from the data distribution, classifier becomes too easy. There's not much signal to the F. So essentially, when you move around, it's really and the same issue we see that in the GAN. So and the GAN has a solution and for WGAN and so on, but this rely, but this one comes out because it's in the high dimension. It's very difficult to start with Q, a good sampling distribution that not far from the data distribution. So therefore, it actually can be quite tricky to apply for the high dimension. For one dimension, it's probably okay. 1D actually, this probably pretty reasonable, or even 2D, right? I think both sample softmax and this can be out, but high dimension, 1Q is hard. Then it's actually not easy. So. Oh, You say whether it's that's a good question. So this one is just one method that we talk about. I'm not sure it's a lot of practical comparisons with these two, to be honest. I would say probably if you just look at the variations of a sample softmax, right, that seems to be used more. So I would say probably that probably will favor, but I do not want to make it a definite conclusion unless I will see more comparisons. But this one is a proposed as a methods, as unnormalized. It's a very well-known method. So we talk about that. And the question is which one is better? Maybe you have some your own data, and then you would compare. Yeah, I would not say, you know, this one just disregard this as not as good. But again, you know, yeah, I guess one can try. But this one definitely is a no method. There are also variations about this, but we won't talk. But definitely it's related to this GAN. Again, this issue is related to GAN because the reason I mentioned this is because, you know, it's a very one nice thing about this one versus a sample softmax. Again, sample is always approximate, right? It's not exact, but this one, if your Q is close enough to your density, this is the exact formulation. So this is a certain nice thing about this, which doesn't exist in the sample softmax. This one, because when we derive that, right, you see the binary formulation, you can learn exactly. Yeah, there's no approximation. So, but really, the practically that one can ask. So I think the main thing is similar to the GAN, right? The GAN, if I can have a good proposal really close to this data distribution, then probably I can run GAN very well from that as well. The reality is, you know, it's a not. So basically, yeah. So this is a key issue about this thing. Yeah. So if I would say all these problems, right? So I can give a summary, right? So MLE is favored. I would say favored loss. The reality is if you have an energy-based model, it's I mean, if you cannot do the normalization, right, then it's very difficult, right? When you do the normalization, then you have to sample sum over every possible, right? And then you have to have a sampling algorithm, right? Sampling algorithm is you have this CD is but again CD you know, has been around for quite a while. And as one the method people want to work with energy-based model, energy-based model is a lot of attractiveness because of probability model, but because of this difficult both learn and sample. So therefore, you know, it's a less, I would say, I won't say it's not used, but I would say it's less used than some other methods like a GAN, right? Like a diffusion model. Both are generator based. You directly apply generator, you generate samples. Here, the things are much trickier. Always approximation. When you're sampling, you have to approximate MCMC. When you are do a computation maximum likelihood, because you involve sampling, you also have to approximate. Sample the softmax is one way to do. I mean, especially for the discrete setting. Discrete is something called large vocabulary. And this actually, this particular formula shows up. This is one of the papers which in the reference, large vocabulary, you can sample instead of, say, using, let's say, 1 million of our vocabulary, or even 100,000. You could possibly sample that, but you could possibly doing all the summation where you could just sampling according to your frequency of where it's more likely to happen. And then you do the sample the softmax. So essentially softmax is a good surrogate which approximate MLE. Because of the adding a stability term, it makes it somewhat stable. NCE replaced this maximum likelihood estimate with data versus noise, surrogate loss. This one compared with the CD and sampled softmax, the advantage is it's precise, but then the disadvantage is probably more sensitive to the Q function, right? So the proposal or noise distribution. But a variation of these exists. So if you're interested, you get the idea, you can see the different variations. But both are the no. And this roughly covers the ones we want to work directly learn the energy-based model. Next time we will say, okay, we can learn score. Actually, once you learn the score, you can say the gradient of the energy scores. You can also try to learn energy, but usually people just stay with the score instead of the energy itself. So next time we'll talk about that. And here are the few papers related. Sample max is again using large vocabulary, which has the formulations, and certainly all the contrast loss paper are related to that, right? NCE is well-known methods. You can which I mentioned, but there's a drop. This is before GAN, so that's why GAN is probably after that, and the contrast divergence is pretty recent. If you think this one is a Langevin, right? And actually, it has reasonable good citations, but as far as I can tell, it's not that stable, so it's hard to use. Okay, in high dimension at least. Okay, that's all. Yeah, for today.